Alright, so as promised, I'm going to attempt to solve this question here, number 63 on page 544, using Kirchhoff's voltage rule and Kirchhoff's junction rule. So you see the information that's given here. I've rewritten it in blue a little bit larger, easier for me to work with. And so I'm going to start off here on the next slide with the junction rule. So at the very first junction, so this guy right here is what I'm working with, J1. I know that the current from the source, IS, which will be this guy, is going to equal the two currents added together here. And I'll just set these directions. As you know, it doesn't necessarily matter what direction we set them in. We can rearrange them later if we need to. So I'm going to say that the I at the source is equal to I1 plus I3. Some information that's given to us, I1 we see here that it's 4.0 amps, so I'm just going to substitute that into my equation. So IS is going to equal 4.0 amps plus I3. And now I need to start looking at my loop rules, and this is going to take a little bit of extra space, so I might just start another slide here. So my first loop rule is going to start at this junction here, and I'm going to work my way around. I'm going to go through the top part here of the circuit, of the parallel part of the circuit, and then work all my way back around to that original junction. Hopefully I didn't just make a mess of it here. So loop 1 is going to equal, and oh sorry, forgot my direction for my actual loops here, this way and this way, clockwise as we've been using so far. So because my current one is going through my loop in the same direction as I've chosen for my loop, it's going to be a negative. That's just the convention set. So negative I1 R1 as it goes through the first resistor, negative, again, same current is going through, I1 R2, continue through the loop here all the way around, and I'm going to go through the battery from a negative to a positive terminal. So that's going to give me a positive 15 volts is going to equal 0. Then I can work with this a little bit more. I know that R1, according to the givens, R1 is equal to R2. So essentially what I have here is negative 2 I1 R1. I'll just use R1 because, again, it's the same as R2. And I can set my 15 volts on the other side of the equation sign, so it's minus 15 volts. I can cancel out the negatives, and I'm left with 2 I1 R1 is equal to 15 volts. If I bring the 2 over, I divide by 2 on both sides. I get I1 R1 equals 7.5 volts. Now what that tells me is that there is voltage at the first resistor of 7.5 volts. And what's interesting is knowing Ohm's law, that volts is equal to current times resistance. I know that my R1 and my R2 have the same value. That was given to us right here. I also know that it's the same current going through it. So if I multiply the same current by the same value of a resistor, I'm going to get a voltage, and I'm going to have it twice here. So if I just clean this up slightly, and apparently that's not working. All right, I'm still figuring out how to erase off of my picture here, and it's not really working out for me. Anyways, what I've solved with the 7.5 volts at I1 R1, it's the same as I1 R2. So essentially this means right here I've got 7.5 volts, and I've got 7.5 volts here at those two resistors. And that should make sense to us. It was given to us that the voltage at the source was 15 volts. We also know that each branch of a parallel circuit gets the same voltage. So if you start off with 15 volts at the junction here, it's going to go through the top branch. Let me choose a different color to show you maybe a little bit more clearly. How about a pink? As the 15 volts of energy per charge starts here, it's going to distribute through this top branch here, and go in this direction, and it's got to drop off all of the energy that it has to keep our loop rule equivalent, equal to 0. So 15 volts here has to drop off 15 volts across the two resistors, again 7.5 each. My next loop is the inner parallel loop, and I'll look at that on the next slide. All right, my next loop, my loop 2, starting at the same junction here, starts off and I have a negative I1 R1, just like before, negative I1 R2, like before, and then I start coming across a current that is in the opposite direction of my chosen loops. That's going to become a positive I3 R3, positive I3 R4, all this equals 0, and it's R3 twice, sorry, I3 twice here because it's the same current that's going through those two resistors. And we also know that I1, R1, we just calculated those to be 7.5 volts. So I can rewrite this to simplify it a little bit and say negative 7.5 volts, because again, the loop rule is trying to figure out how much voltage this whole circuit has, or in this case, the parallel loop of the circuit. I1, R2, again, has the same value as I1, R1 because our R1 and R2 are equivalent. So once again, minus 7.5 volts plus I3. R3 was given to us as 150 ohms. R4 was given to us as 200 ohms. All that equals 0. So once again, I'm going to group the like terms. I'm going to send my two voltages on the other side of the equation sign. I'm going to have I3, 150 ohms, plus I3, 200 ohms, equals positive 15 volts. If I group the like terms here, this is just like in math where you have 2a plus 2a gives you 4a. In this case, we have 150 I3, 200 I3 together grouped gives me 350 I3 equals 15 volts. If I divide both sides by 350, divide by 350, I'm running out of room here, but I get an I3 equivalent to or equal to 0.04 amps. So if I recap what I have from the start, my first junction rule was, what did I have here? IS equals I1 plus I3. I1 was given to us as 4 amps. I3 we just calculated to be 0.04 amps, which makes IS equivalent to 4.04 amps. We can now calculate the total resistance in the circuit because we have voltage at the source given to us as 15 volts. We just calculated current at the source as 4.04 amps. And as we know, resistance is equal to voltage over current. In this case, 15 volts over 4.04 amps. And we get a current at the source, a resistance at the source equal to, so this is resistance equal to 3.71 ohms. Next on the to-do list is to sort of recapture what I've solved so far. I know that my I3 is 0.04 amps. I figured out my V1 is equal to 7.5 volts. I figured out my V2 is equal to 7.5 volts. I guess what's left to be solved is my value for R1 and R2. Luckily for us, they're equivalent according to what was given to us. So if I choose I1 and V1, then I should be able to get R1 using Ohm's law. So my I1 value, which was given to us as 4 amps, so maybe I'll write Ohm's law first here for resistance. For resistance. So R1 is going to equal V1 over I1. If I plug in those numbers, V1 was discovered to be 7.5 volts divided by I1 given to us as 4.0 amps. I get a resistance of 1.875 ohms, and the book told us, the question told us R1 is equal to R2, and that equals 1.875 ohms. Then I'm going to solve for, even though the book doesn't ask us for this is good to know, my voltage at resistor 3 and my voltage at resistor 4. voltage at resistor 3 is going to equal the current 3 times resistance 3. Current 3 we had discovered was 0.04 amps. Resistance 3 was giving to us as 150 ohms. Multiply these two, I get 6.45 volts. Voltage 4, same formula, except I'm going to use resistors 4's value. This is 0.04 amps times 200 ohms. I get 8.6 volts. If I actually round this value, 6.4 volts, 8.6 volts. If I add those two together, 6.4, 8.6, added together gives me 15 volts. And hopefully by this time you've realized that that makes sense also, because looking at the circuit, the bottom branch of the parallel circuit should give us a voltage drop of 15 volts also. Last thing I'm going to do is, as I should always do, double check your work. Make sure that the numbers actually match up here. And I'm going to do that by checking the resistance. So, starting off with total resistance in this circuit, 1 over RT. I'm using this because it is a parallel circuit with the two branches. That should equal 1 over, and if you recall, we're going to add the resistors 1 and 2 together because those two resistors are in parallel to each other. So they need to be added normally, just like your regular resistors in a series circuit. But because the whole series branch is in parallel, that's why it is now a denominator, or 1 over that particular denominator. I'm going to do the same thing with the resistors 3 and 4. Again, those two are in parallel, so I'm going to add those two together to get my resistance for that branch of the parallel loop. We have resistor values for R1 and R2. We found those to be 1.875. Added together gives me 3.75. And that's in ohms, plus R3 and R4 were given to us from the question itself, so together those made up 350 ohms. All this together gives me 1 over RT. At this point, I'm not going to look for a common denominator. I'm just going to turn it into a decimal, and it's going to look like this. 1 over RT equals 0.266 over ohms. The denominator is still, or sorry, the ohms unit is still in the denominator, and that should make sense because our RT is in the denominator. Plus another decimal, quite small one because it's divided by 350, 0.029 again per ohm. Added together, 1 over RT equals 0.269 per ohm. You can flip these two fractions, you can cross multiply, do what you got to do to get the answer. RT equals 3.71 ohms. If you look back in this video, you'll see that our resistance at the source was exactly what we calculated here, 3.71 ohms. I'm going to issue the challenge of looking at the answers in the back of the textbook, and you'll see that they're completely different to what we have here. I believe the resistors were solved as 55 ohms for R1, 55 ohms for R2, and then the current 3 was 0.0, I think it was 7 and something. Anyways, very different answers. My challenge to you is use those numbers given to you, the answers numbers, and plug them into your equations and see why they don't make sense. See why when you add things up, it doesn't give you the proper values, and why the ones that we've just solved for here are the proper values. In the next video, I'm going to solve it avoiding Kirchhoff's long equations, and just by kind of common sense and knowledge that we've gained from looking at circuits.